Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have Stephen Morris here from Princeton. He's going to be talking about robust mechanism design, talk for Microsoft Research.
All right. Thank you very much for the invitation. It's a lot of fun being here, also tomorrow. So I guess this is going to be a multidisciplinary audience, and there'll be some computer science here. So let me put it in a little context of how economists and computer science might think about mechanism design. Of course, economists and computer scientists come from their different perspectives, as you'd expect. Okay, so economists kind of think about incentives, and they tend to focus on and specialize on incentives. Computer scientists tend to think about computational constraints. They tend to focus and specialize in that. And then there's a whole lot of interaction between the two, which people have been studying in recent years, and there are lots of interesting questions that come up with the interaction. So this difference in perspective seems entirely natural and entirely healthy. This is just the nature of the disciplines that we have. Okay? On the other hand, there are very different attitudes about beliefs and Bayesian assumptions and things like that, which is a little more troubling in some ways. Okay? So economists often take subjective or objective expected utility maximization as kind of basic in the analysis of behavior in two senses. Both, it's basically the standard definition of what rational behavior is, the notion of rationality as consistent behavior, and in the face of uncertainty, if you satisfy some reasonable consistency axioms, you should be an expected utility maximizer. And we also take it as a benchmark model of behavior. Okay, clearly people aren't always rational, but this is the benchmark that we like to use. Okay, and many computer scientists wonder where these beliefs are supposed to come from. We have worst case analysis. There's less beliefs floating around, and these different perspectives create some sort of conceptual and other barriers which, unlike our basic focuses, don't seem to be intrinsic. I mean, it doesn't seem to be necessary that these things are here. Okay, so I'm going to give a talk today, and one purpose of the talk is that I'm going to talk about some recent work that I have with Dirk Bergerman that we've been doing over the last few years on what we call robust mechanism design, by which we mean relaxing some of the implicit and explicit assumptions about beliefs within the classical economist conceptual framework. Okay, so it sort of touches on this previous question. We want to relax the assumptions, but we're still very much coming from this economist perspective. So potentially it should make some interesting connections. Okay, other objectives of this talk. Dirk is going to be here in April,
Common knowledge.
talking about some ongoing work that we have on robust predictions in games with incomplete information. This actually kind of follows on from the work that I'm talking about today, and Dirk likes to send me in advance to warm up the crowd. So. Okay, one thing that I'm going to spend a little bit of time on, a little bit of emphasis on, is giving some background and history about economists' treatment of beliefs and higher order beliefs, incomplete information in game theory and mechanism design. I mean, it's relevant for the material with Dirk that I want to talk about. I think that it's also actually relevant for this sort of conceptual barrier here. It's useful to kind of understand where this is coming from. The history is, this background's a little weird in some ways, but it helps to understand maybe the sociology or the history of how economists tend to think about things. Okay, finally, I would like to try and make some connections to computer science work on mechanism design, I talked a shorter talk, but about some of the same material at a computer science economics conference in Cornell this summer. And I was back-to-back talking with Jason Hartline, and he was talking about his work with various co-authors on prior free approximations to optimal mechanisms. Both of us were somehow removing beliefs, relaxing assumptions about beliefs, although there didn't seem to be a lot of direct connections between what we were doing. I'll try and at the end to talk about this a little bit, just to put things in context, to at least be able to say how this connects. Okay, so that's the objective of the talk. So basically, I will go through a little bit of this background material. The focus of the talk is going to be on settings, mechanism design problems of a certain type. The certain type is where you have a planner who's trying to implement a social choice correspondence. I'll be formal about this later, but the important point at this point is that it's going to be a 0-1 objective, where we're going to say, we're trying to design a mechanism, there's something that we're trying to achieve, either you achieve it or you don't achieve it, okay? And it's going to be captured by a social choice correspondence. So in that sense, it's a 0-1 objective. An example would be trying to achieve an efficient allocation, as the planner would be the classic economic example. In terms of this sort of theme that I want to emphasize about relaxing assumptions about beliefs, something important to note is that in this setting, the beliefs that the planner or designer has about what's going on are going to be irrelevant. I don't even have to make any assumptions about that. Okay, so we're just going to focus on the beliefs.
You'll tell us why that's a 0-1 objective, right? Because I would think that it could be somewhat efficient, but I'm probably just not understanding your terminology. That there are degrees of efficiency.
Well, but I'm just going to have theorem. One could define degrees of efficiency.
But what just going to be for it's either efficient or it's inefficient.
Exactly.
Okay.
Yeah. So in this context, and this will be the main part of my talk, I'll be talking about the beliefs of the agent participating in the mechanism, and we bypass the issue of what the planner or designer believes. Okay. When you start look at more general objectives, one would be if you did have a notion of partial efficiency. The classic example would be revenue maximization, where you're really trading things off. Okay, in this case, when we talk about beliefs, we'll have to deal with the question of what the planner or designer's beliefs are. And I'll talk about this briefly at the end, just in terms of trying to understand how things fit together. Okay. Okay, let me just give you a very quick statement of where we're going. I'm basically going to talk about results from two papers that Dirk and I have done in recent years. And so a brief summary that won't be completely clear now, but just to give you some idea of where we're going. We're going to be asking, in this context of social choice correspondences, we're saying, when can we find a mechanism that delivers outcomes that are consistent with a social choice correspondence, something that you're trying to achieve, where we allow for all possible beliefs and higher order beliefs that players might have in the environment. Okay, so relaxing assumptions about beliefs in that sense. Okay, but relatively undemanding, it's going to ask this is kind of the standard mechanism design approach in economics. We can ask, is there some equilibrium that delivers that outcome? Okay, and we'll have an answer, which is that in a certain class of environments that I'll define later, there is a result that says that this question, can you find mechanisms that will work independent of the beliefs and higher order beliefs, does correspond to a well-known belief-free notion of incentive compatibility. Okay, it's going to be equivalent to saying, can I satisfy an ex post incentive compatibility condition that doesn't refer to beliefs? Okay, but this result is kind of restrictive. It's not always true. Okay, so that's going to be the punchline there. And then I'll compare that with the question, when can we find a mechanism that delivers outcomes consistent with a social choice function for all beliefs and higher order beliefs in all equilibria? Okay? And the bottom line is going to be that you're going to certainly have to satisfy the same conditions that you satisfied up here, but there are going to be additional substantive restrictions, and the content of them is going to be that there can't be too much interdependence in agents' preferences. Okay, so these are going to be the flavor of the formal results that are coming. Okay, okay. All right, are there any questions? People tell me that it's a very talkative crowd. I like talkative crowds.
He was telling me not to ask questions. Okay, but.
All right. All right, so this slide describes the basic general environment that I'll be using throughout the talk to talk about. Okay, so think about a setting where there's a finite set of individuals, set of agents, 1 through I. Okay, each agent has a payoff type, which I'll call theta I, which is some kind of parameter that's going to characterize information that it's going to be something that player I knows and that's relevant for characterizing his payoffs and perhaps other people's payoffs. Okay, so a payoff type profile is a vector specifying a type for each agent. There's going to be a set of social outcomes, set Y. Okay, the social outcomes could include allocations of private goods as well. Okay, this is the sort of abstract statement. And each agent is going to have a utility function that says as a function of the social outcome and the payoff type profile, what's the utility that he gets. Okay. Notice that in this formulation, in the general setting that I study, we're going to allow for interdependence, which means that player I's utility can depend not only on his type, but also on other players' types. So in that sense, there's interdependent preferences. Okay, and basically, all of this should be understood, will be understood throughout the talk to be commonly understood among the players, okay, which is itself, is imposing a bunch of structure on the problem. Okay, but I haven't said anything about beliefs here. Yeah.
UIs are known to everybody, for instance. That's what.
Yeah.
So the UIs are known, and my zeta I is not necessarily known. That will involve beliefs, but my big zeta I is known to everybody.
Exactly, yes. So you know your own theta I, but you don't know other people's theta I's.
But
And you know the function, but you don't know the realizations.
Mm-hmm.
Okay?
And will you explain to me why UI squared is not a utility function?
Why UI?
What?
Squared is not a utility.
Oh, yes. I'm going to be doing expected utility maximization. And with expected utility maximization, the cardinality of the utility function matters. So I'm not going to be talking about that in the talk. But given that I assume that somebody is an expected utility maximizer, you do the utility function is uniquely defined up to an affine transformation. So U squared wouldn't do.
Just to give me some sense on why are we distinguishing social outcomes from the payoff type profile?
Social outcomes are the outcome in the payoff type profile is a statement about preferences, how people feel about the outcomes. The social outcome is what's the physical outcome in the world. An example may help. Just think about a classic example that economists study, computer scientists looking at mechanism design study too. Just think about a simple problem of allocating a single good to a bunch of people. They have private values, forget this interdependent business, and quasi-linear preferences. There's money. Okay? So this would be a special case of this framework. It's going to be a special case that I'm going to keep coming back to illustrate points about the general framework. The payoff types are going to correspond to people's valuations of the object. Okay? So player I's possible valuations or payoff types are going to be numbers between 0 and 1. A social outcome is going to be this object here. All I'm saying here is that if you are the planner deciding on a social outcome, what do you have to decide? You just have to decide how to allocate the object across individuals. Okay, so I can think of that as just a probability distribution over agents who I'm going to give the good to. Or maybe I could give the good to nobody, which is why I have the empty set here. Okay, and it's a quasi-linear environment. There's money as well. So we could also give different amounts of money to the different individuals.
But it's just a single good, so you just have one.
That's just one unit of one good plus money.
Delta stands for the set of probability distribution on the set which is in parentheses.
Correct.
So the cross RL is not in parentheses. So the
Correct.
social outcome is a probability distribution on who gets it and also how much money I want to give to
Exactly
each person.
right.
But there's no probability distribution in that.
Yeah, it really doesn't matter. If I put a probability distribution on that, given that it's money that's entering utility into preferences, it's not going to make a
What are
difference.
his units of money anyway?
No, because he takes expectations.
So
it's going to go right through.
So it's not a big deal. Okay, so a typical element of the social outcome is going to consist of the allocation of the good, the amounts of money. The allocation is being described in probabilities. The amount of money is a vector of real numbers. Okay, and utility function is utility function that I get from social outcome y at payoff type profile theta. Now it looks like this complicated object, but it just says theta I is the valuation that he attaches to the object, so we multiply that by the probability that he gets it plus xi. Okay, so usually when you see this problem, you don't see it written in all this general notation. Okay, the only reason I'm writing this classic problem in this general notation is just to see how it fits as a special case of this framework. Okay?
Actually, then there is no interdependence in this.
Exactly. So this is a private value example, meaning that it only depends on theta I. So in my general framework has interdependence. This is private values with no interdependence, this example. Okay. So what I'll call the naive Bayesian approach to incomplete information that sort of bothers some people is to say, well, the natural way to model this, if we want to say you don't know the other guy's playoff types, well, one way of modeling it, a way that economists often use, is to say, well, let's just assume that there's a common prior assumption. That is to say, there's a prior probability distribution over the payoff types, okay? And implicitly, it's being assumed here that there's common knowledge among the agents of what that common prior assumption is. There's some process by which the types were drawn from. Okay, people are going to, their beliefs about other players' types are going to be determined by Bayes' rule. Okay, and then we apply the solution concept of Nash equilibrium appropriately defined for incomplete information in this context. Okay?
Now I have a problem because maybe your allocation rule is not linear. It's in sort of the linearity of expectation you can't use anymore to get. So when you had outcomes, right, you were sort of choosing certain outcomes with certain probabilities.
Yep.
But now if the distribution, but you have not yet said that the guy who does the mechanism design will have sort of some linear function, choose some linear function of this piece to actually design what he gives whom.
Yeah, I haven't
But if
described the
that's-
mechanism yet.
If the mechanism is not linear in the piece, then the fact that there's some probability distribution of the piece and we only have
The mechanism designer is only going to be able to specify what happens as a function of what the agents tell him. He doesn't know the payoff types, and therefore, in order to generate the outcome, we're going to combine this description of what he does as a function of what they say with the probability distribution, and in that way it'll end up being linear. Yep. Okay. Why is this so popular? An interesting observation is that prior to the late 1960s, it was considered a damning critique of the economic relevance of game theory that you acquired common knowledge of the structure of the game, even though that common knowledge would never exist in practice. Okay, so game theory was a very interesting subject studied in math departments, okay, but it didn't have a lot of influence in economics until the mid-1960s. Okay, John Harsanyi in the mid-1960s, late 1960s, revolutionized game theory in economics. He won the Nobel Prize for this contribution, roughly speaking, for making the following observation. Okay, the observation is, I think it's kind of cool, by the way. I'm not meaning to trivialize it. By making the observation that it is without loss of generality to assume common knowledge of the structure of the game. Okay, this whole thing that people thought was kind of nutty. Okay, Harsanyi argued, no, actually it's without loss of generality to make that assumption if, and this is a big if you allow for a rich enough description of the beliefs and higher order beliefs of the agents. Okay, so all you need is a rich enough language so that anything that wasn't common knowledge can be embedded in a rich enough description of the agents. Okay?
The common knowledge here is referring to this distribution P, or is it more?
Common knowledge it'll become clear later. It's referring to, it is the case that when I gave this naive description, we were assuming common knowledge of this P. So in the richer type space that Harsanyi had in mind, the analogous thing will be common knowledge. Yeah. Okay. So let me tell you how this argument goes. Okay. And it was later formalized, by the way. Harsanyi gave a relatively informal statement of this. It was later formalized in the following way. Look, you're worried about the fact that there isn't common knowledge of the structure of the game. Okay. But let's just represent everything that could happen in the game in terms of players' beliefs and higher order beliefs about other players, and come up with a rich enough description of the game, and then this rich enough description of the game is just sufficiently rich that it's tautologous that this description of the game is commonly understood. Okay, here's how the argument goes. Okay, define a type of an agent to be a list consisting of, first of all, we want to specify a payoff type for the agent. Okay, call that agent I 0th level type. Ti0 in the set Ti0, capital Ti0, which is the payoff types of the agents. Okay, what else would we have to specify if we didn't know anything about the beliefs? What else would be relevant here if we were taking a Bayesian view of the world? We'd want to specify a first level type, okay, which is going to be a description of, well, we'd better include the description of his payoff type, but also a belief. I'm always using this delta as probability distributions over a set, a belief over the 0th level types of the other players. Okay, that's what this notation means. This is the cross product over other players' 0th level types, which in this case is just their payoff types, and so on. Second level type, theta I, and so on. Okay? So then we have a type that consists of this countable list of all the beliefs and higher order beliefs at all levels. Okay? Now there's going to be some, I'm giving a sort of informal description here, but there's going to be some restrictions that you'll want to impose on these hierarchies in order for it to make sense. Okay, so I said that you had this 0th level type, first level type, a second level type, but for a type to make sense as a description of a Bayesian person, these different levels had better be consistent in the appropriate way.
Right? I mean, assuming that you have this language is...
Well, I'm not assuming, it's not an assumption about the world, it's just saying, I'm just saying this is a language for me, the analyst, to describe the situation. Okay?
Good.
Now you need actually infinitely many bits, well, not only bits, but infinitely many.
This is a very nasty mathematical object, and computationally it's not going to be well behaved. Okay, so we're going to want to put some restrictions on this. We have these beliefs at different levels, but they have to be consistent with each other. In particular, the payoff type at each level has to be the same payoff type. So formally, the coherence condition that you'd want to have is that you have to say that Tik plus 1, which remember was on theta I cross T minus Ik, if you project it down onto the lower level, which is this object here, you would want it to give you the same Tik that you had before. So you want to build in some coherence up hierarchy. Okay, suppose you do that. One question that you could ask is it the case that you've captured all relevant uncertainty here? I mean, I've described your uncertainty up to a countable number of levels. Does that exhaust all your uncertainty? Well, you can show that there's a certain sense in which you do. Okay. That is, if you look at the space of all coherent types of agent I, okay, it does exhaust all possible uncertainty in the following sense. You can construct a homeomorphism from the set of types of agent I, okay, which is just this collection of types that are coherent in the sense that I described, to the product space of payoff types and beliefs of the types of the other players. Okay? And it's going to preserve beliefs in the sense that under this mapping, beliefs are going to be preserved in the natural way. So your beliefs over a set in the original space.
I see. And the separability is going to be with respect to the topological space here.
Mhm.
the separability that you mentioned earlier.
Which separability?
So you mentioned something in the beginning about there had to be some assumption of separability. So I'm wondering, are there any assumptions on this topological, on this space that you are constructing here?
Yes, so we have to put some topological assumptions on the theta I, on the original set of payoff types. So in the original Mertens-Zamir paper, it's assumed to be a compact metric space. We'll assume standard properties of probability, which is countable additivity. With countable additivity and the topological assumptions, this is actually just an application of Kolmogorov's theorem that says when you specify the beliefs on every finite cylinder, you've specified the beliefs on the limit. Okay.
So you have no events at infinity, which you sort of sometimes say in probability spaces.
Exactly. But this is a
That happens
consequence.
a lot in reality, right?
Well, it's...
I mean, when you have, so when I'm looking at a physics model and I have some long-range order in the system, if I'm looking at simple models in which I might or might not have an infinite cluster, which would be the way I might measure whether I've got some order which is spreading through the system or not, those events are only measurable at infinity.
But that probability distribution could be determined by all the finite.
Oh, it's just determined on the finite cylinders. Okay, so the distribution is determined on the finite cylinders. But you could then still allow those or not?
Probably somehow means that his probability space is eventually the back or something like that.
There are lots of subtleties in this construction. I'm going to be talking about more simpler things, I guess. Okay, so one way this is understood is to say that there exists a universal type space which can be used to describe all certainty that the players might have, all beliefs and higher order beliefs. To make this a little bit more precise, let me define what I mean by a type space.
Okay, so I think that you're okay. I think even if you are generated by the finite cylinders, you can still have these events coming out, the kind that I hoped would correspond to a phase transition. Anyway.
Okay. So let me describe a type space, which are going to keep reappearing in this talk, which is so forget the hierarchical construction for a second. This is just a class of objects for describing uncertainty, which is kind of the, it's presented a little differently, but it's a kind of language that economists use a lot. Okay, so a way of describing uncertainty is to say there's a set of possible types for each player. So Ti is the set of player I's possible types. And each type, I want to understand it to include a description of that type's payoff type. So I have a function mapping each type to the set of possible payoff types. And for each type, I want to specify in addition what's the beliefs of that type about the types of others. Okay? So a type space is just going to be this collection where Ti is just an abstract set describing possible states of mind of player I. And part of the state of mind is a specification of what his payoff type is and what his beliefs about the types of other players are. Okay, now we could construct a zillion different type spaces, but a particular type space is what we call the universal type space, which is the type space that I constructed back here. Okay, the type space where we had the set of I's types is the set of all coherent types. And for each coherent type, we specified there was one payoff type and there was one belief type. That is a belief over the payoff, that is a payoff type of player I and a belief over the types of other players. Okay, and every payoff type and every belief type are consistent with each other. Okay, so we have this notion of what an arbitrary type space is, but we have this observation that there is this space. It's very big. It's an example of a type space, but we call it the universal type space. Why do we call it the universal type space? Because any other type space that I wrote down, I could embed in the universal type space in a natural way. Okay, in particular, I could map it under this homeomorphism that I described to a subset of the universal type space. Okay, and so in particular, the universal type space, and this is going to be important in things that I say later, the the universal type space can be understood to be the union of all possible type spaces. If something is true for all possible type spaces, it's going to be true for the universal type space. Okay? So this is Harsanyi's idea. Okay, and now if you say, back to the question of what's common knowledge, okay, the argument is that, the modern formalization of Harsanyi's argument is that it is without loss of generality to assume that this universal space is common knowledge among the players. Okay, why is it without loss of generality? Well, there's no content in the assumption that everybody understands this space. It's just the expression of what their beliefs and higher order beliefs are and a way of writing it down. Okay, so it's just a way of writing down what their lack of common knowledge is, if you like. But it does translate into common knowledge of the structure of this type space. Okay?
So there's an assumption that there's a common knowledge which is sort of finitely described. That would be very strong.
He doesn't say it's
Yes.
finitely described.
Right. So something that you can study is what's the property of those types that are generated from finite type spaces, and they're kind of special. Okay, now, but let's go back to this naive Bayesian approach. I said that somehow Harsanyi's observation over here, historically, it suddenly made people comfortable doing this. Okay? Now, that was a little bit of a non sequitur, actually. Okay, that is, we were worried that you're assuming too much common knowledge about the world. So Harsanyi says, no, it's okay. If the type space is big enough, it's okay. Okay, but then what people generally do is do this, which is not working with the universal type space. It's working with a much simpler type space. Okay, so a way of saying that is to say the following.
So wait, why is it not working?
So I'm saying
He's saying it's much
this is a very big space. This is a very special space. Okay, so it's very restrictive.
That depends how big theta is.
Yeah, it does depend how big theta is.
So if theta is big enough, this should contain everything.
Yes, I could, but the okay. So what I want to say is that if I take this general description of a type space and I want to map it back into what I call the naive Bayesian approach, I would do it by imposing extra restrictions on the type space. Okay, one restriction is the common prior assumption, which is that all players' posterior beliefs are generated by Bayes updating from a common prior. Okay, that's what this says. There is a prior over the types such that this is the conditional probability of type profile t minus I given ti is generated by these the common prior here. Okay, the other assumption that's implicit in what I call the naive Bayesian approach is that for each agent I and each payoff type, there's exactly one possible belief over the types of the other players. Once you know his payoff type, it's like once you know his valuation of the object, it tells you what his beliefs about the other players' valuations are. Okay, that's implicit in the way I wrote down the naive Bayesian approach, but it's not in Harsanyi's universal type space. That's an extra assumption. Okay? That's the sociology of how people think about it. Okay, so when graduate students in economics first see this, and they're kind of uncomfortable about it, and people say, "Well, it's okay because Harsanyi did this, and there's this universal type space, and it's okay." It sort of creates a comfort level, but it's not quite right in the following sense. Harsanyi is right that assuming common knowledge of the structure of the game, including the type space and beliefs of others, is without loss of generality, modulo some type restrictions. Okay, he's right, but it doesn't justify restricting attention to very simple small type spaces and assuming that payoffs determine beliefs. That's where the content is coming from. Okay, and more content is coming from the common prior assumption. Okay, and of course equilibrium is a strong assumption too.
Wait, why have you told us before? So was the sentence payoffs determine belief mentioned before?
Yeah, I said that implicit in the naive Bayesian approach that I wrote down was the assumption that for each agent I and each payoff type, there's a unique belief that you have.
And certainly that doesn't have to be the case.
Right. I mean, typically when we write down a model of allocating a single object, you assume a prior over that single object, so it generates that property. It's implicitly assumed.
Non-invertible function.
Absolutely. Okay. So, the work that I've been doing with Dirk Bergman and the 2 papers that I'm going to be talking about is going to be trying to keep the Bayesian approach, taking Harsanyi at his word that we can keep the Bayesian approach and it is without loss of generality, but not making these implicit small type space assumptions. Okay? We want to claim that this is the appropriate formalization of something that people talk about in the economics mechanism design literature, is that we have to relax implicit common knowledge assumptions in mechanism design. Okay, so here's what I think Eric Maskin dubbed this the Wilson doctrine. So he says game theory has the great advantage in explicitly analyzing the consequences of trading rules that presumably really are common knowledge. Okay, you can really specify what's going on eBay. But it's deficient to the extent that it assumes that other features to be common knowledge, such as one agent's probability assessment of another's preferences or information. I foresee the progress of game theory as depending on successive reductions in the base of common knowledge required to conduct useful analyses of practical problems. Only by repeated weakening of common knowledge assumptions will the theory approximate reality. Okay, so what I'm trying to say by this introduction is that relaxing this small tight space assumptions is relaxing the implicit common knowledge assumptions. Okay, that's where the implicit common knowledge assumptions enter. Okay?
So wait, and the small type space, was that the same as the 2 assumptions as?
Yeah, I'm
or
payoffs
only
determines
one, only
preferences.
the first one.
Payoffs
And
determines
so-
preferences.
Right, okay.
The common prior assumption is another assumption on top of
another.
that, which I'll talk about a little bit also. Okay, I mean, one thing that we'll see is that our focus is on relaxing the small type space assumptions, but one thing that we'll see is that when you do that, it sometimes removes the extra bite that you get from the common prior assumption and equilibrium. That is, sometimes, and I'll talk about when, common prior assumption and equilibrium only are such strong assumptions because you're in addition making the small type space assumption. Okay, they don't have any bite if you're not making those assumptions. So I think that these implicit common knowledge assumptions corresponding to being Bayesian, but Bayesian on a small type space, is where a lot of the action is. Okay, so that's the background on modeling beliefs. Okay, so now let's be concrete about I haven't described mechanism design yet. So now let's be concrete about the mechanism design problems that we're looking at. When do I talk till, by the way?
How much we interrupt you, but it, I don't know, 5:20, but if we're really obnoxious, then 5:30.
All right.
Okay.
So,
Or if we're really interactive, 5:30.
all right. So as I mentioned at the beginning, I'm going to focus on social trace correspondences, or a 0-1 objective. What does that mean? That means suppose that there's a planner out there who has a correspondence F. So for each payoff type profile, there's going to be some set of outcomes that is going to make the planner happy. Okay, and other outcomes aren't going to make the planner happy, and we want to see if we can make the planner happy. Okay, so.
He's never happy with the empty set.
Yes. Well, he could never achieve it if we had the empty set, because something would always happen. But yes. Okay, so examples. Well, one important case to mention is that the planner might be really fussy and might insist on a unique outcome for each payoff type profile. Okay, so then I would call it a social choice function. So that's just a special case, like a single valued correspondence. Okay, a couple of examples. Let me mention a couple of examples that are going to be important and classic examples. One is efficient allocations. Okay, so just go back to the single object example and suppose I don't care about monetary transfers between individuals, but I want to make sure that the object gets allocated to the guy who values it the most. Okay, so this is a standard objective in mechanism design. Okay, so this is just a formal description of that objective. It says, at theta, the set of acceptable allocations are those where somebody gets the object, We don't want to give it to nobody. And if you give it to I with positive probability, it better be the case that his valuation is at least as high as everybody else's. Okay? Standard set of efficient allocations. Another example that's going to be relevant is budget balanced efficient allocations. Okay? So suppose it's the case. So efficient allocations, we're saying I don't care about moving money around between individuals. Okay? Budget balance says there's a certain amount of money there and I can't throw the money away. I can transfer the money between individuals, but I can't throw the money away. Okay, so that's just saying adding on the extra requirement that the sum of the amount of money that people end up with is constant. Okay, independent of theta. So those would just be examples. Okay, I said this before. The beliefs of the agents are important. The beliefs of the planner are going to be irrelevant here. Okay, so first question that I'm going to talk about is the following. Let me say it in words first. When does there exist a mechanism, a game designed by a planner, such that whatever the agent's beliefs and higher order beliefs about other agents' types, this should say their payoff types, there is an equilibrium that's consistent with the social choice correspondence, that is, that delivers something consistent with the planner's objectives. Okay? To state this formally, let me introduce and review some definitions. Okay, so a mechanism just consists of, for each player I, a set of possible messages that they could send, and as a function of profiles of messages that they send, which outcome gets chosen. Standard definition of a mechanism. Type space, I already told you. Okay? Equilibrium. We're going to look at equilibrium. Notice that if you give me a type space, one of these objects, and you give me a mechanism, one of these objects, if you put the two things together, we have a standard game of incomplete information. Okay, that is to say, there's a set of types of the players, for a set of actions that they can take. Given the actions that they take, there's a set of outcomes, and so on. Okay, so it's a game of incomplete information. So a strategy, this would be a behavioral strategy for player I, would say as a function of your type, what probability distribution over messages do you have? Okay, and then we will say that a strategy profile is an equilibrium. This is just the standard definition of equilibrium in the slightly wacky notation that I'm using here. Okay, but this is the standard definition of equilibrium. It's just saying if you send a message with positive probability, it had better be a maximizer of this expression, which just says what's your expected utility, where your beliefs are according to your type in that type space. Your beliefs over the other players' messages are determined by their behavioral strategies, and your expected payoffs depend on what's the payoff type profile corresponding to the player's types, and what are the outcomes generated by the messages. Okay, so just the standard definition of equilibrium. Okay, so the formal statement of the question I want to ask is, does there exist a mechanism M such that for all type spaces T, there is an equilibrium of the corresponding incomplete information game with the property that for every message that gets sent with any message profile that gets sent with positive probability by that type profile, the outcome is one that is acceptable to the planner. Okay? The planner, by assumption, only cares about the payoff types of the players, not their beliefs and higher order beliefs, which made sense in the examples, right? So that's it. That's the question. Yes. I'm going to for most of the talk because it's easier. But at the end, I will briefly talk about more complicated revenue maximization and other objectives.
So the mechanism was a function of the payoff type but not the type space?
No, the mechanism was a function, the outcome in the mechanism would be a function of whatever messages the planner chooses to give them, and these messages could be as complicated as you like. What I said was that by assumption the planner, and this is an important assumption, the planner cares about the payoff types. He doesn't care what the beliefs and higher order beliefs of the agents about other people's payoff types are, okay? And that's important. Okay, so that's a formal statement. What can we say about that? This question. Okay, so if you can do this, I'll say there's robust implementation. I don't have to make unsatisfactory assumptions about beliefs in order to do things. Okay, think about the leading example, efficient allocations. Well, it's obviously the case that in the leading example, the answer is going to be yes. You should know this already. Why should you know this already? Because the second price seal bid auction is going to be a mechanism that's going to do it. Okay? Just because I'm going to do generalizations of this in a second, let me actually describe it, even though you know it, perhaps. So this is the mechanism where each agent bids his value. The object is allocated to the agent with the highest bid, and the winner pays the second highest price. Okay, this is sometimes called a direct mechanism. You just report your payoff type. Truthful reporting leads to an efficient allocation of the object. Okay, here, for simplicity, just assume we allocate the object with uniform probability if people happen to have the same valuation. Okay, and it's a dominant strategy to truthfully report your type, as is well known. Okay, now obviously if it's a dominant strategy to report your type, your beliefs and higher order beliefs about other players' types aren't going to be relevant, so clearly there will be an equilibrium where you play your dominant strategy that will deliver the right outcome. Okay? No problem. Okay? Of course, it's also going to be true that if we more generally had a private value setting, like the example, okay, the answer is still going to be yes, okay, by basically the same logic. Okay, if it's the case that the social choice correspondence, you can come up with a dominant strategy mechanism that delivers the right outcome, then you can certainly satisfy my criterion here. Okay, so dominant strategies is clearly going to be a sufficient condition in a private values environment. Okay? The interesting question is going to be whether it's a necessary condition. Okay? Let me mention interdependent values. More generally, going beyond the private value setting, so allowing people to care about other players' payoff types, in an interdependent value setting, there is a well-known generalization of dominant strategies to interdependent values, which is ex post equilibrium. Okay, so we'll have a positive answer to the question if you can attain the social choice correspondence in ex post equilibrium. So let me define this. A social choice function, remember, was a mapping from payoff type profiles to outcomes, and we say that it's ex post incentive compatible. This is an incentive compatibility condition that does not refer to beliefs. Okay, and we say the social choice function is ex post incentive compatible if you have an incentive to truthfully report your type, whatever you think the types of the other players are. So basically, if you think that other players are going to report their types truthfully, then whatever their types turn out to be, you have an incentive to report your type truthfully. Okay, so this is ex post incentive compatibility. Okay, and I'll say that the social choice correspondence is attainable in ex post equilibrium if there exists a social choice function such that f is epic, it satisfies ex post incentive compatibility, and it's consistent with the social choice correspondence. Okay? Okay, and before I give the example, let me tell you the result, actually. So the result is going to be that if the social choice correspondence is attainable in ex post equilibrium, then there exists a mechanism such that for all type spaces, there is an equilibrium that delivers this outcome. Okay? Now, this is trivial. Okay? It's no more complicated than the dominant strategies example. Okay? You just say each agent reports his type and reports his payoff type. Okay, and the truth-telling strategy profile is going to be an ex post equilibrium. It's going to be an equilibrium on any type space. Okay? Let me briefly illustrate this with a well-known example. Okay, so a simple example where you have interdependent values is just a variant of the private values example that I had earlier. Suppose that we generalize it and say, so as before, your utility is quasi-linear in money, and we're going to care about the probability that you get the object, but suppose that your valuation of the object depends not just on your payoff type, but you also put some weight on the other people's payoff types. Okay, so this might be for informational reasons, it might be for preference reasons, that you put some weight on other agents' payoff types in the mechanism. Okay, there is a well-known mechanism that gets you the efficient outcome in ex post equilibrium. which is the following. It's a generalization of VCG for interdependent values. I haven't put references here. I think it goes back to Kramer-McLean, actually. But anyway, suppose agents, as before, bid what their type is. Again, we'll allocate it to the agent with the highest bid. Okay, but now instead of paying the second highest bid, suppose you pay the second highest bid plus, we want to take into account this interdependence term, so we'll make you pay plus gamma times the bid of all others. Okay, so if I wins the object by bidding BI, that's the biggest bid, what does he pay? He pays the second highest bid, okay, the maximum of guys other than him, plus this extra term characterizing the interdependence. Okay, so you simply report your payoff type. Truthful reporting is going to lead to the efficient allocation as long as gamma is less than or equal to 1. You're not putting more weight on the other player's types than your types, and truthful reporting is going to be ex post incentive compatible in the sense that I described. Okay? So where have we got to? So this question that I posed about can we come up with a mechanism that delivers the right outcome independently of the beliefs and higher order beliefs, well, ex post equilibrium, which has been much studied, is a well-known solution concept, is certainly sufficient for that to be true. Okay? It's not the case in general that there's an equivalence between the question that I asked and ex post incentive compatibility. Okay? So the converse is false. Okay? It's possible to show by example that incentive constraints can be relaxed by having agents report more than their payoff types. Okay, so in particular, it will sometimes be the case that it is impossible to achieve a social choice correspondence in ex post equilibrium, but it will be possible to construct a mechanism where for all beliefs and higher order beliefs you'll get the right outcome. Okay? We can give a sufficient condition when it's tight, though. Okay? A sufficient condition when it's tight, it's kind of messy to write down, but it's going to turn out to be quite simple, really. We'll say that an environment is separable if the outcomes, I can divide the outcomes, I can represent the outcomes as a product space where there's an outcome y0 which you could think of as a social outcome, and there are things that we can think of as private outcomes, y1 through yi. Your utility is going to depend on the social outcome and your private outcome yi, but not on the private outcomes of the other players. Okay? That's what this says here. Okay? And suppose that the social choice correspondence works by specifying the public outcome in y0 is determined by a function. Okay, there's a function that always determines the public outcome. And the set of private outcomes, f1 of theta, this could be f1 could be a correspondence, but the set of outcomes depends, is separate for player 1 and doesn't depend on the private outcomes of the other players. Call that a separable environment. Okay?
You can think about it as a auction so that you can get different goods, different players.
Combinatorial auctions.
Yeah.
So if I modeled a combinatorial auction this way, I would think of y0 would be this richer set of the allocation of the objects across the players. So that would fit.
And now I'm wondering whether there is some other general example in real life that is not combinatorial auction but satisfies the separability requirement.
That does or doesn't?
That is not a combinatorial auction, but satisfies separability.
Well, any quasi-linear environment, well, I'm going to say here that, first of all, any single valued objective is going to satisfy this constraint because you can just ignore these private components. And secondly, any quasi-linear environment, the standard quasi-linear environments that both economists and computer science study pretty often, where the I don't know what that means, where transfers do not affect f. What matters is a quasi-linear environment where the set of private outcomes that are feasible aren't a function of the private outcomes received by the other players. Okay, and an example would be the efficient allocations that I described earlier. So it's not just combinatorial auctions, it's any quasi-linear setting. So public good allocation problem.
Still, you can think about the outcome. The outcome just simply the goods you give to each player and not something.
Yeah.
Seems narrow.
So the combinatorial auction is an example of it satisfies separability. So the ex post incentive constraints characterize this question that I posed. However, a classic example that doesn't satisfy it is simply budget balanced allocation. So that one that I wrote down earlier. Okay, so for budget balanced allocations, it's not the case that ex post equilibrium is equivalent to these solution concepts. Okay. Okay, so we have the equivalence in separable environments between ex post implementability and this question that I was asking. Okay, actually, it's an interesting question. You know, we give a few theorems and some special and some examples, but we don't know a whole lot about how significant is the fact that you can do better than dominant strategies or better than ex post equilibrium in general. It's not quite clear. Yeah.
Additional question, so if it's not helpful, you should ignore it. So I guess when people started studying ex post equilibrium, they kind of had the intuition that it was really nice because it didn't seem to require a lot of beliefs. And so in some sense, from an applied perspective, we're kind of happy with that and just marched on with that. Now you studied this much more carefully, and now you have formalization of when that intuition was basically right.
Yep.
And people can sort of be happy that you verified it and keep marching on. And you've also learned something about the extensive answers which is not right. Can you sort of boil down in a couple of sentences, what you feel like you've added, both in the case where they do match up, as well as the cases where they don't? Sort of like kind of the benefit of the additional formalism. Can you kind of boil that?
Oh, I think that I think that I think that the trouble with trying to formalize these statements is coming up with the right language to talk about it. So actually, I think the main contribution is really just coming up with the right language to talk about it. The separability the separability is a important property. It identifies what is it that really matters for having this equivalence or not having this equivalence. But maybe more important is just having the right language to talk about it. So
it's kind of maybe the intuition that you might gain some intuition about what you were missing in not thinking it all the way through by understanding what the role of separability is. So you sort of said that separability matters, but can you gain any intuition about what you are and are not missing by the fact that separability does matter?
In particular, and this
I'm
is
not sure
just
that I
my lack of understanding, but is separability necessary to getting this or not? I mean, you've been able to prove this under the condition of separability.
Why? By example, I know that you don't, but I don't have a tight characterization of when you get it and when you don't get it. Yeah. So my answer is it's done exactly what you say, which is maybe just formalize and clarify this issue. I think that the question of what happens when separability fails and whether that gap is important, we haven't really said a lot about, but I do think that that's an interesting question. The discussion, I would argue, was actually pretty confused about this issue. So just to give a flavor of the confusion, way back at the beginning of the mechanism design literature, people talked about related issues. Okay, so there are papers that made the point this was in a private value setting where people proved theorems to the effect that if a social choice correspondent must be implemented without knowing the prior, dominant strategies is required, so sort of formalizations of that statement. Okay, but actually what they're assuming is that you had a mechanism that, in the language of this paper, a mechanism that was a function of the payoff types, and the same mechanism as just a function of the payoff types was going to work whatever the beliefs were. Okay? So, but the assumption that if you don't know the beliefs, you're restricted to choose a mechanism that just depends on the payoff types is restrictive. Okay? So, and if you pose the question in general, we've said that the answer is no for social choice correspondences. Okay? The classic counter-argument among the Bayesian purists to these arguments in favor of dominant strategy equilibrium, so it's kind of a folk argument that people would make, one formal reference. But if the agents don't know the prior, if you're assuming that the prior is common knowledge among the players, you could always just ask them to tell you the prior, and if they tell you something inconsistent, you can shoot them or something. Okay? So, so what's wrong with that argument? Okay? I mean, clearly there's something wrong with that argument about using it in practice. Okay? But what's wrong with that argument in theory? Okay? What's wrong with the argument in theory is that the assumption that people were making in this debate that the prior was common knowledge among the player, and the problem was that the planner didn't know it, is missing the point. The point is not whether the prior is common knowledge among the players. So we would say that it's the wrong question that was being asked. Okay? What's important is that the assumption of common knowledge of a common prior being maintained is not without loss of generality. Okay? And with the right question, we see that dominant strategies is not always required, but it is in many special cases. Okay, I'm running out of time, so let me quickly mention the other question and conclude. Okay, so suppose we want to think about what's sometimes called full implementation instead, which means requiring all equilibria to deliver desirable outcomes. Okay, so there's a literature on this extra requirement, which says that you need some requirements over and above incentive compatibility to make sure that not just an equilibrium delivers the outcome, but all equilibria deliver the right outcome. Arguably, so this has been an important literature. It's one of the things that Eric Maskin got the Nobel Prize for, I guess. Arguably, it hasn't had a huge influence on applied work, among other reasons, because the mechanisms seem to be too complicated. Okay, you know, they're very unrealistic looking mechanisms in order to get rid of the bad equilibria, basically. Okay, so the other result that I wanted to mention.
In those cases, this is just because I don't know anything about it, is there some characterization of the measure of your phase space that will head to the right and the wrong equilibria? You know, because it may be that there's a bad equilibrium out there, but that the conditions such that you would be driven to that bad equilibrium are vanishingly small in some sense. And you know, so in a dynamical systems problem, you would look at the measure of the phase space, which leads to the good and the bad equilibria.
Yep.
And here I just wondered whether anyone had
I don't know results quite like that. I mean, maybe the closest thing is that there is a literature on saying refining the notion of equilibrium, so selecting among the equilibria, saying that if I use the stronger solution concept, then I can get stronger results, which you can do. Okay, so another question that you can ask is, so I guess just illustrating this approach a little bit more, is combine the requirement that I said before, I want the mechanism to work for all beliefs and higher order beliefs, with the requirement of full implementation, so I want to have for all equilibria. Okay? And by putting the two things together, it turns out you get some clean results. Okay? So the question is, when does there exist a mechanism such that whatever the agent's beliefs and higher order beliefs about other agents type, every equilibrium outcome is consistent with the social choice function. Okay? So we've upped the ante a little bit here. I'm going to focus on social choice functions here rather than correspondences. We've seen that correspondences, you already have problems just with incentive compatibility, just with getting an equilibrium. Okay, so let's focus on the well-behaved case of a social choice function. Okay. Okay, so formally, this is the question. Does there exist a mechanism such that for all type spaces and all equilibria, we have this property? Okay. So just to think about this question, let's go back to the single good allocation problem. Okay, notice that robust implementation is going to fail even in the private values case, since truth-telling is only a weak best response, and there are many equilibria leading to inefficient outcomes in the second price auction. Okay, and in fact, you can't achieve robust implementation in this sense in the single object auction, even if you allow more complicated mechanisms than just the second price auction. However, you can perturb it a little bit, so you can get an almost efficient allocation, and with an almost efficient allocation, then under private values, and if there's not too much interdependence in preferences, you can get robust implementation. Okay, so I want to describe that to you in the example, and our results for general settings are just appropriate generalizations of what happens in the example. Let's see why that's the case. Okay, so a kind of standard and not very deep observation is that although there are many equilibria in the second price auction, if I perturb it a bit, I can make sure that there's a unique equilibrium. Okay, the perturbation is going to make it not quite efficient, but it'll make it strictly dominant strategies to choose the right thing, and that'll make sure that there aren't bad equilibria. Okay, so how does that work? Suppose that we look at the second price auction where you bid your value. With probability 1 minus epsilon, we'll allocate it to the highest bidder and pay the second highest price. With probability with probability epsilon, I'm just going to pick one of the players with uniform probability and just conduct a mechanism that will give that player an incentive, a strict incentive to truthfully report his type. Okay, a mechanism that does that is that I say that you bid something and you will get the object with probability bi, and you will pay a half bi for the object, and that gives you an incentive to truthfully report your type in this extra epsilon part of the mechanism. So you make truth-telling a strictly dominant strategy, so then the epsilon efficient allocation is robustly implemented. Okay, so in the private values case, there's a very small cost in going to full equilibria. There's some kind of perturbation thing. Okay? But let's think about the interdependent case. This is where we're going to get something more interesting happening. Okay? The same sort of logic goes through in the following sense. You can say with probability 1 minus epsilon, we'll do this interdependence adjusted VCG mechanism. Okay? And with probability epsilon, we'll do this other thing where we give you an incentive to truthfully report your type. And then I can make truth-telling to be a strict ex post equilibrium of the game. Okay, but here's the complication. In the private values case, where I got truth-telling to be a strictly dominant strategy, I said, well, that just obviously means that every equilibrium is going to deliver the right outcome. Okay, that's true. If you have a strictly dominant strategy, then whatever your beliefs and higher order beliefs, you will always have an incentive to tell the truth, so every equilibrium will deliver the right outcome. With interdependent values, that's simply not true. The fact that there's a strict ex post equilibrium doesn't mean that there can't be other equilibria that deliver the wrong outcome, and in fact there are. Okay, so that's a difference with the interdependent values case. Okay, and in fact the result is going to be that this particular mechanism that I wrote down, the modified VCG mechanism, is going to deliver the right outcome only if the interdependence in players' valuations is sufficiently small. Okay?
Well, there was something before. I mean, it was just kind of a stupid thing. It was that gamma had to be less than 1 or something, right?
Right, which you required actually even for incentive compatibility.
Even for incentive compatibility, because otherwise, you know, if I place more store on what somebody else cares about than what I care about. And here, somehow with the interdependence, it's saying that it's only if I'm placing really very little store on the sum of, it makes some sense that it should scale like 1 over L because you've got a sum of 1 over L other terms there,
Yep.
of L other terms there, right?
Yep.
So this seems to be very much an analog of that.
Right.
Yeah.
I mean, one way to think about it is that we know that with private values, if you perturb it, you can do it. So it's sort of continuous, saying there's a neighborhood around private values if the interdependence is sufficiently small. Okay. However, if the interdependence is bigger than this constraint, then not only does that mechanism that I describe not deliver the right outcome, but no other mechanism, however complicated, will not deliver the right outcome either. Okay. So however complicated the augmented mechanism that you come up with is.
What happened at equality?
It's included. No
Yes, but
mechanism.
I'm
It's
curious
included.
whether there's something particular happening there.
You'll see.
Is this true even when you don't, even when other people can inform on you?
Absolutely. This is all mechanisms in
Okay.
which people can inform on you any way you like.
It's not only I know about my preferences.
No, this is incomplete information. So only you know your payoff type. Okay, but it is the case that other players can report anything they like. I don't know if that answers your question.
So this is not for incomplete information series.
This is for incomplete information sets.
Sure.
Yeah. Okay, well, here's an interesting observation. I think I'm just going to have time to sort of talk about it informally. But I think that it's kind of an interesting observation. The question here was saying, when is it the case that I can find a mechanism such that all equilibria for every type space deliver the right outcome? Okay? Intuitively, solving for all equilibria of every type space is going to be a complicated thing to do. Okay? But the good news is that there's actually a much simpler expression of what can happen that kind of corresponds to having a more demanding solution concept. In fact, the solution concept is a variant of iterated deletion of strictly dominated strategies. Okay? So a key observation, which isn't just for this example, it's true in general, is that a message MI can be sent by an agent with payoff type theta I in some equilibrium on some type space, if and only if that message MI is incomplete information rationalizable in the following sense. That is, if and only if MI satisfies some other solution concept, a rationalizability solution concept. What's the solution concept? Suppose that we do an iterated deletion process where we start off by saying let every payoff type send any message, okay, and then progressively delete those messages which are not a best response. There should be a not here. Delete those messages that are not a best response to some conjecture over the payoff type message pairs of the opponents that have not yet been deleted. So you iteratively delete messages. So there are no beliefs in here, right? This is a solution concept, an incomplete information version of rationalizability, no beliefs, strictly dominated, to do with iterated deletion of strictly dominated strategies. I could have taken this solution concept as given, as my theory of behavior. What I'm saying is that you can show that it's equivalent to the question that I posed, what can happen in any equilibrium on any type space. So in that sense, equilibrium no longer has any bite once I have these richer type spaces. Okay? This is related to a literature on epistemic foundations of solution concepts in game theory. Okay? So I'm really out of time, and I wanted to talk about this stuff at the end. So let me just quickly give you the flavor here and move on. Okay? So here's the idea. The basic idea is going to be the following. Suppose it was the case that agent I conjectures that other agents' types were theta minus I, but he thought that they were going to misreport their types to be theta minus I prime. Okay? Then the linear structure of the game is going to guarantee that player I's best response is going to be to report theta I prime. Okay? If he was sure how they were going to misreport, this is how he would want to misreport. Okay? He wants to adjust his report for their misreports. Okay? So the linear best responses are going to guarantee that if I do this iterated deleting of messages, at each round there's going to be an interval of misreports that each agent could send. And in general, they're going to be shrinking. Okay? So just take my word for it that at each round there will be an interval. Okay? Now the key trick, what you were saying about adding up across the I-1 agents, that's where it comes from. Yes, that's definitely where it comes from. Okay? So you can write down an expression for how these upper and lower bounds at each round are going to work out. Okay? But the key observation is going to be, well, let's look at this expression here. If you're saying what's the upper bound at the kth level, okay, forget this min expression. It's going to say that what's going to matter is how big was the deviation at the k-1th level, and multiply that by gamma and multiply across all players. So that's gamma times I-1. Okay, so as a consequence, if we ask the question, what's the upper bound on the misreport of agent I and the lower bound on how much he's misreporting, at every round you're going to be multiplying by gamma times I-1. Okay? Now, obviously, if you're multiplying, if we're looking at this gamma to the I-1 over k, it's going to be rather important whether gamma times I-1 is bigger than 1 or less than 1. Okay? So if gamma is less than 1 over I-1, this process is going to converge and we're going to get truthful reporting.
It's much less obvious to me why the minute is bigger, so here it is.
Okay. So here's the argument. Suppose it is the case that gamma was bigger than or equal to 1 over I-1, and the inequality case is covered here. Suppose I said that we're allowing for all possible beliefs and higher order beliefs that players might have. Okay, so suppose in particular, yes, I construct them. So suppose in particular that type theta I was convinced that other players' types were this exact formula here. Okay, now the important thing about this formula here is that 1, I fixed it, and 2, it has the property that that when my payoff type is high, I'm convinced that other guys' payoff types are low. Okay, so basically my beliefs about the other guys' types are going to compensate for the difference in my type. And as a consequence, if you ask, if I have these beliefs, what's my valuation of the object? It's actually independent of my payoff type, because I think the other guy's payoff types are adjusting for mine. But that means if everybody had these beliefs, they have identical preferences. And if people have identical preferences, you might get lucky and they might play differently in an equilibrium. So you might be able to find an equilibrium that delivers the right outcome. In fact, we know you can in this example because I proved you a theorem about that. Okay, but if they have identical preferences, you can't guarantee that in all equilibria. There's always going to be the possibility that they'll behave the same way, and then you're in trouble. Okay, we've got to be using the fact that gamma is more than or equal to I minus 1 here. Where did we use that, by the way? We used that in constructing this expression here. This expression wouldn't be possible if gamma was bigger than or equal to I minus 1, because I would require these theta j's to be outside the bounds of possible.
And I see the n in all equilibriums as the difference between having a fixed point theorem on a compact space where I know there exists at least one fixed point, but only if I have a contraction do I know it's a unique one.
Yes. So in fact, we call it, so the general theorem, we describe a property of having not too much interdependence, which we call the contraction property. But I'm going to skip this because basically what we have is a generalization of this example that gives the observation that robust implementation is possible if and only if there's not too much interdependence, which in general is formalized with a contraction property characterizing the amount of interdependence in players' preferences. Okay, so let me conclude by just saying a few words about revenue maximization. Okay, so suppose that in the leading example I had the planner wanting efficiency or budget balance efficiency, the 0-1 objective, but of course another question that you might want to ask is what if you wanted to maximize revenue subject to some participation constraints? The classic revenue maximization problem. So some people do. So if you're going to be a Bayesian here, you're going to have to worry a little bit, not just about the agent's beliefs and higher order beliefs about their payoff types, but you're going to have to take some position on what the planner feels about the world. Okay, so this is going to be a little bit problematic. Okay, I said I was going to try and relate. So Silvio has work that's somehow related to. So I know a little bit more about this Hartline work. I don't know how much is going to apply to Silvio's work, but okay. So some of this work by Jason Hartline takes the following approach. So talking about the revenue maximization problem. So talking about basically this problem. Okay. So what do? They say let's restrict attention to mechanisms with dominant strategies. Okay, by assumption. And also assume that the seller doesn't have beliefs over the agent's payoff types. Okay? And then look for mechanisms that achieve tight bounds on the percentage of some benchmark revenue. So like in the example, it would be the second highest valuation of the agents that's attainable. Okay, these are remarkable results, and I think that this kind of stuff should be incorporated into economics. Economists should know more about it. I think that one reason why they don't know about, one issue that I tried to mention at the beginning is people sort of think about things in such a different way, it's a little difficult to see the connection. So it would be nice to sort of understand a little better. I think that some criticisms which economists make is the restriction to dominant strategies does not have a Bayesian foundation. Okay? So this is related to Susan's point earlier. I mean, people are pretty happy saying dominant strategies ex post seems to capture the idea that it doesn't depend on beliefs too much, and that's a good thing. Okay, in this context, in this context of revenue maximization, it's not the case that my theorem, the theorems that I talked about apply, and we don't know that you couldn't do better taking a Bayesian point of view, even without making the implicit common knowledge assumptions, than assuming dominant strategy. So that's one connection. I mean, you don't have to answer that question, but I'm just making the point that in terms of the relationship, that question is not addressed, why we assume they have to choose dominant strategies. Okay, another criticism is that the benchmarks might seem a little ad hoc. Ad hoc is a favorite expression of economists. It's an insult. But I think that at least sociologically and maybe substantively, something that's important to get across to economists is to give you some principled reasons for why this is the objective. Economists really care about the objective. Okay,
Why don't you say instead of ad hoc, pragmatic?
Well, that would give a different feel, wouldn't it? So recent work is actually pulling things together a little bit. They're actually relating these benchmarks to what's the best thing that you could do if the prior was known, and that's starting to give a little bit more of a foundation. I think this is very nice, in that it, I think that's a good direction for them to go if the objective is to get economists involved. Okay. By the way, there is some work. There's a paper by Ili and Chung, which does talk about foundations for the dominant strategy assumption in this setting with revenue maximization. Okay. So, in a rather special class of problems, so it's kind of a mystery to me why it has to be so special, but in a special class of problems, you can show, so it's single good allocation problems, and you need that it's the Myerson's regular case, where you have strictly monotone allocations. They pose the following question. Suppose the seller has beliefs over agents' payoff types. Okay, so unlike Jason, they're going to assume that the seller has some beliefs of his own over the payoff types. Okay, but he picks his mechanism not knowing what the beliefs and higher order beliefs of the agents are. Okay? So in particular, he picks the mechanism that maximizes the minimum of the revenue that he could get for all possible beliefs and higher order beliefs of the agents. Okay? And under some fairly restrictive conditions, you can show that this reduced to dominant strategies.
To be safe.
To be safe. But so I guess the
Makes
reason
it a
why
much weaker result.
the reason why I want to mention this result is just to make the point that there is a bunch of intermediate things that you can do. There's the question of this guy's beliefs, this question of that guy's beliefs. This guy is somewhat Bayesian in that he has a belief about the agent's payoff types, but he's somewhat worst case in the sense that he looks at the worst case over the possible beliefs and higher order beliefs. But there's sort of a continuum of things that you can do, and I think it's kind of worth exploring. Okay? A different set of questions that you could ask, I told you I was going to introduce Dirk's talk in April. So a different kind of question that you could ask is the following. Suppose you maintain the common prior assumption, unlike Ili Chung, but you could ask the following question. Suppose a planner, we could actually think more generally, an econometrician observing the world, has some beliefs over the payoff types of the agents. Okay, so like Ili Chung, we'll have that bit of Bayesianism in it. And he knows that it's common knowledge among the agents that this is the true marginal distribution over the payoff type. So everybody knows that this is the true probability distribution over the payoff types. Okay, but the planner, or in this other interpretation, the econometrician, does not know what the agent's beliefs and higher order beliefs about the payoff about their payoff types are. So each agent knows that ex ante this was the true marginal distribution over the payoff types, but they could know everything about the other guy's payoff types. They might know nothing about the other guy's payoff types. All kinds of things are possible. You can ask the question, what's the set of observable behavior in a given game or mechanism that the planner or econometrician could observe? Okay, so Dirk's going to tell you the answer. This is another example of sort of considering intermediate assumptions about beliefs. Okay, so I'm going to conclude here just by saying that it's a tricky question thinking about how to model beliefs. That there are lots of intermediate approaches that you can do. One, I think that it is important to understand that economists' obsession with Bayesianism, that there's a lot of room for maneuver within that, in the sense that you can maintain a Bayesian view of the world, but you can stop making a lot of the implicit assumptions that seem to come with it, and you can go a long way doing that. And this might make some connections, for example, with how people who are less sympathetic to having beliefs look at things. Okay? In the simplest case, that is partially or fully implementing a social choice correspondence, we're able to give some reasonably crisp characterizations of the effect of relaxing the implicit common knowledge assumptions. Okay, I think the big deal for the future, we did this social choice, what I talked about today was the social choice correspondence case and a pretty extreme relaxation of common knowledge assumptions. Okay, you know absolutely nothing about the beliefs and higher order beliefs. You could consider intermediate cases. I think that for economists this will be important. They're not ready to give it up completely, okay, but we can get much more realistic results by doing something intermediate. Okay, I've tried to describe to you why revenue maximization is a harder environment to work with because it raises this issue of the planner's belief. So both conceptually how to formulate the question and solving the questions that you end up formulating is harder in this case, but the returns are pretty high to understanding it. Okay, and there would be a lot to be learned by combining different approaches. Thank you.
Stephen, I have a
Of course.
So how about our setting in which there is a prior, and the play is common knowledge to the players, but the designer has no idea about it?
Mm-hmm. I think that that's
how
actually.
does this fit in?
I think that that's related to my discussion earlier about some of this prior literature. I guess we don't need the slide. Oh, okay, there they are again. I messed it up. Okay, so it relates to this discussion earlier about, you know, some of the debate within economics mechanism design about dominant strategies versus Bayesian equilibrium. That's actually the way the question has been posed. People assume that this prior is commonly understood among the agents, but the planner doesn't know it. My personal view is that this is just a mistake going down this road. I mean, people talk about this problem and talk about detail-free implementation where you're maintaining the assumption that there's common knowledge of the prior among the players, but the planner doesn't know it. I think that you know, the results that you get out of that may be appealing from a practical point of view. Okay, from a theoretical point of view, it's not very satisfactory. Okay, for the reason that I gave earlier, that if it really is common knowledge among the agents of what the prior is, if you took that seriously, you really should be able to get them to report their priors and shoot them if they're inconsistent. Okay, so you don't get. So I mean, maybe you like the answers that you get by thinking that way and constraining the mechanism, but if you allow general mechanisms, I don't think that that particular set of assumptions is particularly insightful. I don't think there will be common knowledge of the common prior among the agents anyway, so.
I was actually asking in relation to the other iterative deletion of a strictly dominated strategy, because if you allow people to report a common prior and you shoot them, there is the possibility that of having several equilibria, right, in which there are several priors that these guys can become. But instead, I was wondering if somebody has thought about anything about combining this common prior with instead this belief-free de facto solution concept of a new iterative deleted dominated strategies. Because in that case, you know, I'm saying I would not necessarily be convinced that reporting the common prior and shoot them is a good solution. Because not for the
Sounds like your
purposes.
kind of solution, Silvio, actually.
Well, in the harshness perhaps, but not in the meaningfulness, because, you know, all of a sudden, you know, there are going to be plenty of other equilibria there. How the hell I know which is which? And it's very easy that, you know, maybe I believe that some equilibrium will arise, but I don't know how do I know it is really the truthful one, except that maybe it's going to be simple to tell a reporter the truth rather than concoct a lie. But
Right.
short
No.
of that. But maybe combined with these other belief free things, right, then it may actually be a reasonable model, even theoretically, if you combine it with a solution concept that is either headed division. But I don't know.
Yeah, I agree that if you require full implementation, all equilibria deliver the right outcome. If you weaken the solution concept to iterated deletion, you could go down all these routes to try and kill the report your prior equilibrium. They would go in that direction.